This is our second lecture for this particular section. So we're focusing on Lewis structures, two lectures for this, and then we'll do a few for molecular geometry and molecular polarity. So for Lewis structures, we were looking at chemical bond formation, bonding in Lewis structures, the octet rule, and exceptions to the octet rule. That was in the first lecture. This next lecture, we're going to be looking at formal charges, resonance, and drawing Lewis structures and practice drawing them. Okay, so let's look at formal charges. So let me grab the right set here, and here we go. So atom formal charges in covalent molecules and ions. So the goal is to understand the meaning of atom formal charge and calculate the formal charge on each atom in a molecule or polyatomic ion. So, formal charge, it's the charge on an atom in a molecule or polyatomic ion if all shared electrons are split equally. So I want you to take a look at this Lewis structure for a hydrofluoric acid. So notice that the hydrogen has 2 valence electrons, just like helium. The fluorine has 8 valence electrons, just like neon. So these two atoms are fairly stable because they have valence electrons equal to the noble gas in their group. Normally, that's going to be an octet. Hydrogen is an exception. Now, if I split these two apart and take these 2 electrons and give one to hydrogen and one to fluorine, we ask ourselves, what is the charge on this atom formally if it has 1 valence electron? Well, if we go back to the periodic table and we look at hydrogen in group 1A, it has 1 valence electron. So that's a neutral atom. So what is the charge on this hydrogen atom with 1 valence electron? It's neutral. How about this fluorine with 7 valence electrons? Well, if we take a look here, with 7 valence electrons, it's neutral. So this is also a charge of 0. So normally in these guys, when you split them equally, hopefully you end up with a formal charge of 0. So let's take a look at this with O2, which has a double bond between the oxygens. When I split this up, this has 4 electrons. 2 have to go to this oxygen, and 2 have to go to this oxygen. So here I have a non-bonding pair called a lone pair, another non-bonding pair called a lone pair. And when we split these up, half of these become a non-bonding pair on this oxygen, so to speak. Now, it's not really a non-bonding pair. The important thing is there's 6 electrons. How many valence electrons does a neutral oxygen atom have? Well, it's in group 6A. It has 6 valence electrons, so the charge, the formal charge is 0. So formally, this oxygen has a formal charge of 0. This one's 0. So it's judged by comparing separated electrons on atoms to the number of valence electrons in the neutral atom. There's an actual formula for it where the formal charge is equal to the number of valence electrons in an atom minus the lone pair electrons and also minus half of the bonding electrons. So here's an example where we have this, this is called a hyperchlorite ion with a -1 charge. And this is the Lewis structure. Now, I haven't shown you how to get to the Lewis structure. This is the Lewis structure. You're just going to accept it for now. And here you can notice that each atom has 8 valence electrons. The oxygen has 8 because you include that bond. The chlorine has 8 because you include those 3 bonds and that lone pair. Again, a lone pair is a non-bonding pair of electrons. Lone pair, like the Lone Ranger. Okay, so this chlorine has 8 and each oxygen has 8. You want to get good at counting pairs and counting 2s and 2s and 2s and making sure that for each line you count 2 electrons. So everyone has its octet, so it looks like the noble gas in its period. Now, when we deconstruct this, this oxygen gets 2, 4, 6 plus half of these, so it ends up with 7. Oxygen normally has 6 valence electrons to be neutral. When you add another electron onto it, it becomes -1. So that's why I have a -1 here for the formal charge of this oxygen. Now, how is this oxygen any different from this one? And the answer is it's not. it will also have 7 valence electrons and have a -1 formal charge. All of the oxygens, in fact, have a -1 formal charge. The chlorine, on the other hand, has 5 valence electrons and normally has 7. So what's 7 minus 2? 5, right? So that's how we get the 5 here. So here, to get to a 5 valence electrons, you have to take away 2 electrons. When you take away 2 electrons, what happens to the charge on this? It becomes +2. Now, if you've done the formal charges correctly, you'll notice that the formal charges, when you add them all up, -1, -1, -1, and +2, which add up to -1, all the formal charges add up to the charge on the ion or molecule. Now, using the formula, here's how we get the formal charges. So notice I drew an oxygen atom in here with a lone pair, lone pair, lone pair, and a bonding pair. So here's how we use the formula. Oxygen is in group 6A, so the number of valence electrons is 6. How many lone pair electrons? 2, 4, 6. So lone pair electrons is not asking how many lone pairs, it's asking for how many lone pair electrons. It has 3 lone pairs, but it has 6 lone pair electrons. So we use the number 6 here. How many bonding electrons? Well, it has 1 bond, but there are 2 electrons. So we put a 2 there. So half of 2 is 1. Oh, and this should be a plus. So we have 6 plus 1, and that becomes a -7. 6 minus 7 is -1. And for chlorine, we do the same thing. We have 2 plus 3, which is 5. 7 minus 5 is +2. So you can assign formal charge by doing this deconstruction and looking at what you get compared to what it should be if it were neutral, or you can do this formulaic way. This formulaic way kind of takes away from the understanding behind the formality of this. It turns out that we can't just take atoms apart in a molecule and say, oh, here's your charge. That's not the way it happens. Okay. Now, how do we use formal charge when we're looking at Lewis structures? Well, the best Lewis structures have atoms all with a formal charge equal to 0. So that can happen with molecules because the formal charges, if they're all 0, it adds up to 0, which is the charge on the molecule. If you have a polyatomic ion and it's, say, a -1, you have to have at least 1 formal charge of -1. So that's the best you can do. Now, if you do have a formal charge and you don't like formal charges more than -1 or +1, if there's a positive formal charge, you want it to be on an atom with smaller ionization energy and smaller electron affinity. So in a period, you're talking about the ones to the left are going to have smaller electron affinity and smaller ionization energy, or the ones lower in a group. And if you're going to have a negative formal charge, you want it to have it on those atoms with a greater electron affinity or greater ionization energy, which means in a period they're the atoms to the right or the atoms above. So here's an example where we have 3 Lewis structures for this ion. This is the cyanate ion. So notice that in each Lewis structure, each atom has an octet. You might want to pause this and look and count and make sure you get 8 for each atom. And then once you've convinced yourself of that, then I'm going to show you the formal charge on each of these. This oxygen's a -1, this is a 0, and this is a 0. On this Lewis structure, this oxygen's a 0, this carbon's a 0, this nitrogen's a -1. Notice how all the formal charges add up to -1. In this Lewis structure, you've got a +1, a 0, and a -2. Now, of these 3 atoms, which is the most electronegative? The answer is the one farthest to the right, which is oxygen. Which is the least electronegative? Carbon, which is the farthest to the left. Okay, so if we're going to have a -1 charge on this, we want it on the most electronegative atom, oxygen. So that's why this Lewis structure is the best. You've got 2 formal charges of 0, which is great, and you have a -1, a non-zero, but it's on oxygen, your most electronegative atom. What about this one? Well, this one you really do not like because you have a formal charge of 0 on only one atom, and you have formal charges that are not 0 on 2 atoms, so you really don't like this one. What do we think about this one in the middle? Well, it's kind of okay, but clearly not as good as the one on the left. The reason is that nitrogen is not as electronegative as oxygen. It doesn't have as much electron affinity as oxygen. And remember, electron affinity is you want an electron. So since oxygen has greater electron affinity, it would like to have that electron rather than nitrogen. So this structure is more important than this one, and this is the least important. So that's why we have worst, best, and the mid list. And that's how you use formal charge to evaluate Lewis structures. Okay. So next we're going to look at resonance. So for resonance, we want to draw resonance structures for simple molecules and polyatomic ions. And we want to understand what resonance means and how and when to use resonance to represent bonding. So let's give you some examples of resonance. So here, the nitrate ion can be drawn this way. So notice we've got this single bond here, this double bond here, and this single bond here. We have octets everywhere. And this is one of those ones where you have an exception to the number of bonds you normally have. Nitrogen normally has 3 bonds, but here we have 4. Also, oxygen normally has 2 bonds, but here it has 1 and here it has 1. Only this oxygen has the number of bonds it normally makes. Okay, so why do we have the double bond here? Why don't we have it here? We could. So let's take a look at that. Here, the double bond is on the left. And we've shoved electrons around a bit, but notice we've got 2, 4, 6, 8 on this oxygen, 2, 4, 6, 8 on this. We've got 8 on each atom. So it could be that the double bond is there. Or it could be that the double bond is on top. Now, if we take a look at this, here's something we have to understand. Double bonds between two of the same atoms are shorter than single bonds. And the way to think about this is not that the electrons take up a lot of space, but the electrons are pulling together the nuclei. Remember, the nuclei repel one another, but the electrons are oppositely charged to the nuclei, so it attracts the 2 nuclei together. The more electrons you have in there, the tighter you can pull those nuclei together. So a double bond should be shorter than a single bond. So when we take a look at this molecule, though, and we study it with spectroscopy, we find out that all of the bonds are the same length. They are not different in size. There's not 2 long ones, the singles, and 1 short one, the double. There's not. Also, it doesn't go back and forth where you have this long bond where it becomes longer and shorter and they go back and forth. That doesn't happen. They're all the same length and this thing is steady as a rock. So what's going on here? Well, what's going on is that none of these resonance structures is absolutely correct by itself. But the way to think about it is that we average them. So this bond is this bond is this bond. They're all the same bond. And if you notice, we've got 1, 2, 3, 4 bonds split amongst 3 molecules. 4 divided by 3 is 1.33. So this bond length is like a 1.33 bond, not a double bond, not a single. What about this top bond? Well, it's an average of 1, 1, and 2, which is 4 bonds over 3 molecules. It's also 1.33. So that explains how all the bond lengths are exactly the same. It's because our resonance structures, none of them is exactly correct, but all 3 contribute to the overall structure of, in this case, the polyatomic ion. So you might ask, well, isn't there a way to draw the atom so you can draw all 3 identical and draw a 1 1/3 bond? How do you draw a 1/3 bond? A single bond is 2 electrons. So 1/3 bond would be 2 divided times 1/3, which is 2/3 of an electron, right? So how do you draw 2/3 of an electron here? And that's a bond. You can't. So you draw the 3 resonance structures. So that's resonance structures, and we will learn how to get to resonance structures when we draw Lewis structures in just a bit. All righty, we're going to take a look now at drawing Lewis structures and how we go about doing that. We've just finished up with formal charges and resonance, and I still haven't shown you how to draw Lewis structures. So now is the time to show you how to draw Lewis structures and take into account the octet rule. Take into account exceptions to the octet rule. Take into account formal charges and take into account resonance. So the goal for this section ultimately was to be able to apply the octet rule when drawing Lewis structures for simple molecules and polyatomic ions. But now it's to also know when you get to have less than an octet or more than an octet, and how to draw resonance structures, and then how to use formal charges to decide if you have a good Lewis structure. So this is a reminder to you about the number of bonds elements like to make. And when we say like, it's usually, because elements don't like anything. So how do you get the usual number of bonds that an element likes to make? It's the number of single electrons in its Lewis dot symbol, or Lewis electron dot symbol. So here, those numbers are the ones that are not in parentheses. The ones in parentheses are the exceptions for the number of bonds they like to make or can make. And remember here, we have krypton is 0 and xenon can make 0, but also can do 4. So this is kind of a reminder to you of what might occur. So here are the guidelines for drawing Lewis structures. And you don't need to apply every rule, because sometimes the answer to the rule is, okay, nothing happens. But let's take a look at the guidelines. First, you want to count valence electrons. If you have an ion and it's a negative charge, that negative charge are valence electrons. So if you have a -1, you have to add 1 more valence electron. If you have a +1, you have to take away a valence electron, because that's how you get the positive charge. You take away a valence electron. You choose a central atom or atoms. And the central atom is going to be one that usually makes the more bonds. That kind of makes sense, right? And the one in the middle is the one that makes more bonds. Or you could say the one that has less electron affinity. Now, what if you have a tie, like you have an oxygen and you have a sulfur, both like to make 2 bonds? Who wins? Well, oxygen's exceptions are 1 and 3. Sulfur's are 4 and 6. Since sulfur's exceptions are more than oxygen's exceptions, you'll put sulfur in the middle. You arrange the rest of the atoms around the central atom using single bonds. And then you place non-bonding pairs on surrounding atoms to get the octet. And you do this 1 atom at a time. And you want to make sure that when you put those electrons down as lone pairs, that you don't use more electrons than you counted in number 1. If you have remaining, if there are remaining valence electrons, you place all the rest on the central atom, all of them. Okay, even if you go more than an octet. So this is one of those places where you may end up with more than an octet. And you notice here, I don't tell you place the remaining electrons on your central atom until you get an octet. I just say place them all there. If the central atom lacks an octet, though, you want to change a lone pair on the surrounding atom into a bond to the central atom until you get an octet on that central atom. And you want to pursue all options. That leads you to possible resonance structures. And then you evaluate using formal charge. So let's take a look at this one by one. These are pretty straightforward examples where when we look at the rules, number 1, count valence electrons. This one we end up coming to a fairly quick conclusion. So let's take a look at CCl4. And the very first thing we want to do is count valence electrons. So we have 1 carbon plus 4 chlorines. Each carbon has 4 valence electrons. Each chlorine has 7, for a total of 4 times 7 is 28, plus 4 is 32 valence electrons. So that's the first thing you do, count valence electrons. Now, which of these tends to make more bonds? And the answer is, well, carbon has 4 valence electrons and it tends to make 4 bonds. Chlorine has 7, but only 1 single. So here, 4 singles, 4 bonds, 1 single, 1 bond. So you're going to put carbon in the middle. And you put the rest of the atoms around carbon with a single bond to them. So that's going to be our central atom. So that's number 2. And then number 3, you place the rest of the atoms around the central atom. And then this is also going to be number 4, because we're going to put lone pairs on the atoms surrounding the central atom until you get an octet. So now that chlorine has an octet. And now that chlorine has an octet. And now that chlorine has an octet. How many have we used so far? Well, 8 here for that chlorine, 8 here for that chlorine, and 8 here for that chlorine. 8 times 3 is 24. 25, 26, we've used 26. 27, 28, 29, 30, 31, 32. So we've used all 32 valence electrons. And we take a look, and we're supposed to take all the extra ones beyond 32 and put them on the carbon, but we don't have any. So we're done here as far as that goes. Now, since this guy has an octet, the carbon has an octet, 2, 4, 6, 8, we're probably pretty good. Let's assign formal charges to each of these. So the formal charge on carbon with 4 bonds is equal to 4, the number of valence electrons on a carbon, minus the lone pair electrons, which are 0, and minus 1/2 of the bonding electrons, which is 8. So we get 0. So the formal charge on this carbon is 0. And you can see that the formal charge on each of the chlorines is going to be the same, because they all have 6 valence electrons that are lone pairs and 1 that's a bond. So these are all zeros. So what do we think of this Lewis structure where all formal charges are 0? Everything has their octet. We love it. This is a fantastic Lewis structure. Only you don't want to leave it looking like this with the charges on it. You want to redraw it so you can see the octets on each atom. And there you go, the Lewis structure. Let's try this now for this NF3. So NF3, a nitrogen plus 3 fluorines, which is 5 plus 3 times 7. 3 times 7 is, 21, plus 5 is 26. So we need 26 electrons. That's the first thing. Second thing, we're going to pick nitrogen as the central one because it likes to make 3 bonds because it has 3 singles in its symbol. So remember, nitrogen looks like this, and fluorine looks like this. 3 singles, 3 bonds, 1 single, 1 bond. So we're going to choose nitrogen as the central, and we're going to put the fluorines around it like this. And then we put lone pairs on the surrounding atoms until you get an octet. And so far we've used 24 electrons. So number 4 says, okay, put the rest on your central atom. We've used 24, we have 26, so I'm going to put 2 more here. And then when we look at this, we see, okay, we've used all our electrons. We do have an octet on the central atom. And now we take a look at formal charges. The formal charge on this fluorine, so I'm going to do this differently. The formal charge on this fluorine is going to be V6 plus half of the bonding electrons. So that's what it looks like. So it has 7 valence electrons. And if it has 7 valence electrons, and it normally has 7, the formal charge is 0. So that fluorine's a 0, that's a 0, that's a 0. And when we look at the nitrogen, it's going to have the lone pair on top, and then it'll have a single, a single, and a single. It has 5 valence electrons, which is what it should be. So that's a formal charge of 0. So all the atoms in here have a formal charge of 0. They all have their octets, and boom, we are done. Okay, let's take a look at another example then. So let's see now. Trying to find my problems here. We just did that one. So now I'm going to place this away, and let's take a look at the next one. Draw the Lewis electron dot structure for thionyl chloride, a reagent widely used in organic chemistry. So let's take a look at how we solve this one. So thionyl chloride, SOCl2. So sulfur has 6 valence electrons. Oxygen has 6 valence electrons. Chlorine has 7, but there's 2 of them. So when we add those up together, we get 12 plus 14, which comes out to 26, right? 12 plus 14. So we have 26 electrons. So that's the first thing. Second thing, oxygen makes 2 bonds normally. Chlorine makes 1 bond normally, and sulfur makes 2 bonds normally. So we have a tie. Who are we going to choose? Well, you choose the one that has less electron affinity, and that's going to be sulfur. Or you could say, look at the exceptions. The exceptions for oxygen are 1 and 3. The exceptions for sulfur are 2 and 4. Excuse me, 4 and 6. 4 and 6 are greater than 3, so sulfur is going to be in the middle, and we're going to put the others around it like so. Now, you could put the oxygen on the left, the right, the bottom, any which way you want it. You could even make this look like a propeller and even them out. It doesn't matter. But here is the Lewis structure to begin with. This is number 2. And then number 3, you're going to do this. Now we're going to put lone pairs on the surrounding atoms. I'd like to start with the one that is most electronegative because it wants electrons more. So here we go. And now you can see that we have what? 24 electrons. So what do we do to finish this off? Number 4 would be you put electrons on the central atom, and that's 26. Now let's evaluate this with formal charges. So when we look at this, the formal charge is going to be as follows. This is going to be a 0. This is going to be a 0. So we should be getting quicker at doing this. We see that this has 6 electrons that belong to the chlorine, plus half of this bond, which means 1 electron. So this has 7 valence electrons compared to 7 that it would normally have. This oxygen would actually be a -1. And this sulfur normally has 6 valence electrons, and here it only has 5. So this is a +1 formal charge. That seems to be pretty good, right? But take a look at this. What happens if I do this instead? I'm going to take a lone pair from this oxygen and move them down here and make a bond. So this is what it looks like now. The oxygen still has its octet. The chlorine still has its octet. This chlorine still has its octet. This sulfur now has 10 electrons. Remember, anything in period 3 or greater can have more than 8. Let's evaluate formal charges here. Well, the chlorine's going to be 0. This chlorine's going to be 0. This oxygen is going to be 0. And this sulfur is going to be 0. Look at the number of bonds this chlorine has. 1. How many bonds does it normally have? 1. Its formal charge? 0. Let's look at this chlorine. How many bonds does it have? 1. How many bonds does it normally make? 1. What's its formal charge? 0. This oxygen, how many bonds does it normally make? 2. How many bonds does it have? 2. What's its formal charge? 0. Look at this sulfur. How many bonds does it have? 4. How many does it usually make? 2. But 4 is allowed. Its formal charge is 0. Look at this sulfur. It has an octet. How many bonds does it have? 3. How many does it normally make? 2. But 3 is not an exception. So this is not your best Lewis structure. This is your best Lewis structure. And this is what you'd want to present as an answer on the test. So you can see that formal charge really helped us out with that one. We also saw how we got a multiple bond. Let's take a look at this one now. Draw the Lewis electron dot symbol for a multiple bond. So we want to do this for CO2. So CO2, you got a carbon plus 2 oxygens, 4 for a carbon, 6 for an oxygen. So this comes out to 16 electrons. You're going to put carbon in the middle. And then you're going to add lone pairs to the oxygen and lone pairs to the other oxygen. Okay, so now each oxygen has 8. Now the question here is, can I just put more lone pairs on carbon? Can I do this? Now everyone's got an octet, and I can't do this because I've used too many electrons. I've used 18. And we only, I've used 20. And we only get to use 16. So you can't do that. So we're stuck with this. So now what do we do when we have this and we don't have an octet on carbon? Well, there are 3 things we can try. We can take a lone pair here and make a bond, a lone pair here and make a bond, and we get this. Do you see how we get an octet on this oxygen, octet on carbon, and an octet on this oxygen, and we still only use 16 electrons? Or you could do the same for this oxygen. You could take a lone pair and make it into a bond, another lone pair and make it into a bond, and you could get this. So that's another possibility. Another possibility is you take one lone pair from one oxygen to make a bond, one lone pair from the other oxygen to make a bond, and do this. So which of these is the best? Well, let's assign formal charges. To this oxygen, the formal charge would be +1, this carbon would be 0, and this oxygen would be -1. The opposite would be the case here. This would be a -1, this would be a 0, and this would be a +1, and this would be 0, 0, and 0. Now what you should do is you should pause this recording and calculate the formal charge for each of these atoms to see if you get these numbers. Now take a look here. Kind of a quick and dirty way to do it, doesn't always work, is just look at the number of bonds it's made and the number of bonds it usually makes. If they match, the formal charge is usually a 0. Carbon likes 4 bonds. This has 4 bonds. Formal charge is 0. Carbon has 4 bonds, usually makes 4 bonds. Formal charge is 0. Carbon makes 4 bonds, has 4 bonds. Formal charge is 0. Oxygen normally makes 2 bonds, has 2 bonds. Formal charge is 0. So both oxygens are the same way. But when you don't have the number of bonds you normally have to make, it's best to calculate the formal charge or figure it out. Okay, so clearly these 2 are not important, and this is the best Lewis structure. Okay, so there's that one. We ended up with 2 double bonds on carbon. So we're going to look at a few more examples here. So draw the Lewis structure for polyatomic ions. So we're going to do this. This is called a hyperchlorate, ClO3, -1. So chlorine has 7, oxygen has 6, and we're going to add one more for the charge. Because remember, to get a negative charge on this thing, you have to add a valence electron. So we've got 3 times 6, which is 18. 18 plus 7 is 25, plus 1 is 26 electrons. Okay, now we have 26 electrons. We're going to put chlorine as the central one. And the reason we put chlorine in the center is because it is the least electronegative. So in this case, we're not going with the number of bonds it normally makes. We're looking with the number of bonds that it could make. And chlorine can make 1, 3, or 5. So that's why we're putting it in the middle. Lone pairs on the oxygens. So now we've used 24 and 26. So now we want to evaluate this. And if we evaluate this, we get a -1 here, a -1 here, a -1 here, and a +2 here. And that all adds up to the -1. So that's not so hot. What happens if we take one of these and make a bond here, and another one of these and make a bond here, and just leave one oxygen without a bond or without a double bond, and we still have 2 here. All right, so here the formal charge is going to be 0, 0, -1, and 0. So if you take a look here, we have 3 formal charges that are 0. We have one that's a -1. We're going to have at least one atom with a formal charge of -1 because of this charge here. So this means we like this pretty good, pretty well, I should say. Now to finish this off, you draw brackets around it and you put a charge on the outside. This is one of the possible structures for this. There are 2 more. Another one looks like this. And what does the third one look like? Well, it looks the same, only the double bonds are between the top and the left. So these are the 3 resonance structures. And this should give you the idea that there are not 2 double bonds and 1 single bond, but rather, if you take a look here, there's 1, 2, 3, 4, 5. There's 5 bonds spread over 3 molecules, which is a 1.67. So each of these bonds is not quite a double bond. It's not quite a single bond. It's almost a double bond. It's a 1.67. And remember, double bonds are shorter than single bonds. So this is going to be shorter than a single bond and longer than a double bond. So these are your 3 resonance structures. So do you remember that part where I said you need to evaluate this and you need to pursue all options for making your structures when we borrow the lone pairs? We have to look at all the options. So I could do it from the 2 end ones here, an end and a top, an end and a top, all possibilities. That's how you get your resonance structures. So these are the 3. And this is something I would expect on the test, all 3 of them. Notice how we draw the resonance structures and the relationship so that we know their resonance structures. We draw what's called a double-headed arrow, not 2 arrows, a double-headed arrow. That indicates resonance structures. So these are resonance structures. All right, let's try this for the nitronium ion next. And I wonder if it has any resonance structures. So nitronium ion, I think this is our first cation. We have 5 valence electrons for nitrogen, 6 for its oxygen, and we have to subtract 1 to get a positive charge. So we've got 12 plus 5, 17, minus 1, we get 16 electrons. So here we're going to put nitrogen in the middle with the oxygens flanking. Then we're going to put lone pairs on each oxygen. And we see right away that we get 16 electrons, and we don't have an octet on nitrogen. So you can see very quickly that the thing that makes the most sense is to make a double bond between this oxygen and this nitrogen by converting a lone pair into a bond, and the same on this side. And of course, we want to put a plus and brackets around it, because you always put a bracket around an ion. And then the charge on the outside of the bracket. So this seems to be the best, because here you get a 0, and a +1 for formal charges. And if you are going to have a plus formal charge, you want it on the atom that is less electronegative, which is nitrogen. So there are no resonance structures for this one. We would discount this. Well, let me ask you, why would we discount this and say, nah? Well, let's look at formal charges. -1, +1, +1. How many formal charges is 0 here? 2. How many formal charges is 0 here? None. So we don't like that. So that's the nitronium ion. All right, just a couple more pages of problems here. So let's try this one. So here we're going to look at another example. Clearly, this is one where the central atom has more than 8 electrons. So let's take a look at this. I don't know the name of this ion, I'll be honest with you. So here, we'd be looking at 7 for chlorine, +7 for fluorine, and then +1 for the charge. So we're looking at 36 electrons, because really that's 5 sevens, so that's 35 plus the 1. So we're going to put chlorine in the middle, because fluorine only makes 1 bond, but chlorine can make 1, 3, or 5. So there we go. And that is 32 electrons. And that would be 36 electrons. Now, because it's an ion, we do this. And let's evaluate formal charges. Each fluorine has a formal charge of 0. The chlorine, let's see, let's count electrons here formally. So remember, we get half of the bonding ones and all of the lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 electrons, should have 7. An extra 1 gives it a -1 formal charge. So here we have 4 zeros and 1 -1, which is beautiful. Now, the thing that we don't like about this is that the -1 is on the chlorine. We'd rather have it on the fluorine, but we can live with this because we have 4 zeros. So here is this ion where you've got more than 8 electrons on the central chlorine. And you'll notice that we don't have the number of bonds we normally like to have here. Here we only have what? 1, 2, 3, 4, and it should be a 1, 3, or 5. We could try to fix this, but if we did, we'd make a double bond here or somewhere like that, and you'd end up with a positive formal charge on fluorine, and that wouldn't be good. So sometimes you have to kind of work the gray area and decide, okay, Maybe I don't have the number of bonds I normally would make, but I do have the negative charge on a fairly electronegative atom. I'll tell you, there's probably more to this ion than we know. All right. So draw resonance structures for the nitrite ion. Are the NO bonds single, double, or intermediate in value? What are the formal charges on the nitrogen and oxygen atoms? So for the nitrate ion, we're talking about 5 electrons plus 12 plus 1 more for that negative charge. So we're looking at 18 electrons. So put the nitrogen in the middle, oxygen's flanking. So there we go. We've used 18 valence electrons, 16, 8 on that oxygen, 8 on that for 16. We have 2 more, so there we go. So now when we take a look, nitrogen does not have an octet. What are the options? One option is to take a lone pair from that oxygen and make it a bond, like I've done there. But what's the other option? The other option is to take a lone pair from the other oxygen and make it a double bond. Now remember this lone pair I had on top. Don't forget about that. And the charge is a -1. So do we have octets everywhere? Yes. Let's look at the formal charges. So you want to try to assign these. Pause this right now, assign them, and see what they are when I write them down when you put play again. Okay, so here they are. -1, 0, 0, 0, 0, -1. Do we like those formal charges? The answer is absolutely, because they're mostly zeros. And when we do have a -1, it's on the most electronegative atom. So we really like those. Now, here, what is the bond? It's an actual average between a single bond and a double bond over 2 molecules. So it turns out that each bond is like a bond and a half. So what does that mean? It's going to be longer than a double, shorter than a single. So this atom doesn't have like 2 bonds where one's long and one's short and it goes back and forth. They're both kind of short, kind of long. Okay. That was the last example. You will be having a lab where you do a lot of this type of work. Thank you for listening.